Hi, and welcome to my talk about CMC surfaces in hyperbolic space. My name is Gudrun Szewieczek, and this is joint work with Udo Hertrich-Jeromin, who is also working at the Technical University in Vienna. Probably you have already seen these examples of curves that are generated via a rolling construction. In this example here, I'm fixing a blue line and then roll that blue circle onto that line. And if you fix one initial point and follow that point during the rolling, then you generate a further curve, this orange curve here. Of course, the geometry of the blue curves, of the curves that are rolling onto each other, influences the geometry of the curves that we generate by this construction. This method can be generalized to submanifolds and in particular to surfaces. And in this talk, we will discuss whether and how CMC surfaces, so surfaces of constant mean curvature in hyperbolic space, can be generated via such a rolling. My talk will consist of two parts. In part 1, I will start with some preliminaries about hyperbolic space and surfaces. And then I will discuss some well-known facts about CMC surfaces in hyperbolic space. And in particular, we will reconstruct CMC surfaces starting from their hyperbolic Gauss maps via a Darboux transformation. This transformation will then be key to success for the second part of my talk, where we will discuss how these CMC surfaces in hyperbolic space can be generated by some rolling. So we will first discuss the general construction of rolling, and we will then generate CMC surfaces in hyperbolic space via such a rolling. So the goal in the second part is to find pairs of surfaces such that if you roll those two surfaces onto each other and choose a suitable initial point, that initial point under the rolling will generate you CMC surfaces in hyperbolic space. When I say surface in this talk, I usually mean a surface patch, and all surfaces are parametrized. So they are given by a map from a two-dimensional domain M2 to an ambient hyperbolic space. And for me, an hyperbolic space is a three-dimensional space form of constant negative sectional curvature. It's important to emphasize here that the theory that I'm presenting is only a local theory. So we are really looking at patches of surfaces that have no singularities and are absolutely regular, and we don't deal with global questions. So this is really a local theory. As a model for our ambient hyperbolic space, we will use the Poincaré half-plane model. So we will consider the upper half space of R3 and equip it with the metric of the following form. In this model, it's in particular simple to describe geodesics. By geodesics, I mean now curves that provide the shortest distance between two given points with respect to the hyperbolic metric. And in our Poincaré half-plane model, those geodesics are then given by circles and lines that intersect the boundary orthogonally. The boundary is here this gray plane, and in our model that's the xy plane of R3. Any surface in hyperbolic space comes with two hyperbolic Gauss maps, and in our model those hyperbolic Gauss maps can be easily constructed via the following geometric method. Namely, we first consider a point on the surface and then construct the unique geodesic that intersects the surface in that point orthogonally. So we are constructing a circle that intersects not only the surface, but also the boundary orthogonally. And generically, this geodesic then has two intersection points with the boundary. And these two intersection points are then 2 points of the two hyperbolic Gauss maps. Of course, by varying the point on the surface, we then get two planar nets on our boundary, and these two are then the hyperbolic Gauss maps. Most of the time, the surfaces in the talk will be parameterized by curvature lines. So this means they are orthogonal and conjugate. And if such a surface is parameterized by curvature lines, then our two hyperbolic Gauss maps are also orthogonal. After these general facts about surfaces in hyperbolic space, I now want to focus on CMC surfaces, so on surfaces that have constant mean curvature. First, I want to briefly mention that there's a huge amount of literature about that topic. This starts from classical works by Dabou and Bianchi, goes to famous Weierstrass representation for CMC surfaces in hyperbolic space. There is great work about singularities that can occur on CMC surfaces. So you see there are many results in various directions. The aspects that are most important for our rolling construction later will be integrable aspects of those surfaces. Namely, one can prove that CMC surfaces in hyperbolic space belong to the integrable subclass of isothermic surfaces. This means that on a CMC surface in hyperbolic space, one can find conformal curvature line coordinates. This means that the first and the second fundamental form are both diagonal, and in particular the first fundamental form is also conformal. If a CMC surface in hyperbolic space is parameterized by these special coordinates, then we can see a special property of one of the hyperbolic Gauss maps. It comes for free that the hyperbolic Gauss maps are orthogonal, since we have curvature lines. But now we know even more. If we have a CMC surface in hyperbolic space, one can prove that then one of the hyperbolic Gauss maps is conformally parameterized. So one of its hyperbolic Gauss maps is conform. And now we can take advantage of the fact that for general isothermic surfaces, there is a well-explored and rich transformation theory available. In particular, the Dabou transformation for isothermic surfaces. And this transformation will allow us to reconstruct CMC surfaces out of suitable hyperbolic Gauss maps. So the idea is, on our boundary of the hyperbolic space, we prescribe one conformal map and then make Dabou transformations of that conformal map to obtain surfaces in our hyperbolic space. And these surfaces will be then CMC in this hyperbolic space. And here are more details on the Dabou transformation. We say that two surfaces f and f hat are related by a Dabou transformation if they satisfy the following conditions. First, we require that f and f hat envelop a common sphere congruence. So this means that the two surfaces are tangent to a two-family of spheres. So f and f hat envelop a common sphere congruence. And this condition induces a 1-to-1 point correspondence between the two surfaces. Namely, two surfaces are in correspondence if they lie on the same tangent sphere in the sphere congruence. And our condition is then that if we move along one curvature line on one surface, then the corresponding points on the second envelope also lie on a curvature line. So F and F hat envelope a common sphere congruence such that curvature lines correspond. And the second condition for a Darboux transformation is a condition for the two first fundamental forms of F and F hat. Namely, we require that with this parametrization that is induced by the sphere congruence, we know that the two first fundamental forms are related just by a conformal factor, meaning that the two metrics are conformally equivalent. So the metric of F equals factor times the metric of F hat. Here are two facts about the Darboux transformation. First one, if two surfaces are related by a Darboux transformation, then they are both isothermic. So if F and F hat are Darboux, then we know that F and F hat are isothermic. So this is indeed a transformation that belongs to the integrable surface class of isothermic surfaces. Fact 2. If we start with an isothermic surface, so if F is an isothermic surface, then one can prove that there exists a 3+1 family of Darboux transformed surfaces of F. Why 3+1? So these three parameters here belong to the free choice of one initial point in R3. And the fourth parameter is a spectral parameter that represents the integrability of this transformation. So for one isothermic surface, I can construct a 4-parameter family of new isothermic surfaces by using this Darboux transformation. Here comes a theorem that is important now for our CMC surface case in hyperbolic space. This theorem was first proven by Bianchi with classical methods and then was reproven about 20 years ago by Hieronymi, Musso and Nicolodi by using quaternions. And the result is as follows. If we start with a conformally parametrized planar net, so in a given plane, which in our case will be interpreted as the boundary of our hyperbolic space. If in that plane there's given a conformally parametrized planar net, that's called N, then any Darboux transform of N either lies again in the plane B, takes values in the plane, so is again a planar net, or the second possibility is that the Darboux transform then becomes a CMC surface in a hyperbolic space. Or is a CMC surface in a hyperbolic space. So this means if we choose one initial point for our Rabu transform that is not in the plane, so for example here, then with that initial point we obtain a Rabu transformed surface that is CMC in an appropriate hyperbolic space form. And this theorem now will be key for the second part of the talk, where we'll use exactly this construction to show how we can construct CMC surfaces via a rolling construction, so by rolling two isometric surfaces onto each other.